Okay, thank you very much. The red light is on. So you heard that we are being recorded for posterity, so behave and especially think twice before asking a question. Now, thank you very much, the organizers of the conference, for the invitation, and the organizers of the whole program for putting in the efforts to making it possible for all of us to meet here now and in the coming weeks. Now, the director mentioned that there are 120 square meters of blackboard, so it would be a heresy not to use one. And after I'll fill these 6, we move to corridor, to library, even to men's room, ladies excused, and then to the first floor, second floor, outside, I suppose, and so on. So I'm going to talk about a certain approach to problems which are primarily in proof complexity, but I'll talk about some complexity issues in general. So the complexity of computations and proofs and pseudo-finite structures. Now, I think that my handwriting is definitely improving with age, but if you think otherwise, feel free to ask me questions at any point. Now, by complexity of computation, it will be clear that we will talk about circuits and circuit.
Earlier recording.
No, you never hear anything twice.
You know, with handwriting, we should be able to compare.
Oh, I see. Then, of course, at least on the first blackboard, it will be definitely much better. So, by computations and its complexity, we will mean circuit size, and by complexity of proofs, we will think about length of propositional proofs. That's the main topics of potential applications. But let me start with what I mean by pseudo-finite structure. Now, I'm not entirely sure if there is actually the official definition of it is. So I will give one, and then I'll change it a little bit to the one I'll use it. So let me have a language, and I will usually assume that it's finite, or at least it's countable and recursive, and it's relational. And I'll say that L structure A, that there are no function symbols, perhaps just constants. Okay, so an L structure is pseudo-finite if and only if it satisfies the theory of finite L structures. And this is in fact equivalent to a simple condition that every sentence which is valid in A holds also in some finite structure. And moreover, this is equivalent to saying that A is elementary equivalent to an ultra product of finite structures. Now, this last characterization is easy to use to get examples of families of pseudo-finite structures, namely any L structure which is an element of a model of the true theory of hereditarily finite set theory, finite sets, is pseudo-finite. And this is equivalent, so you would get an equivalence if you think about being elementary equivalent to such a structure. Now this last thing is equivalent to actually being coded in a model of true arithmetic. Now it may look, because we will talk about some problems about extending such structures and what holds in them and topics like that, it might seem that the best is to look at pseudo-finite structures as on ordinary structures. But in fact, it seems that for the type of reasoning which we will employ, how do I get there? Yes, some tall guy. Well, I'll okay, no, that's fine. Oh, there is actually this this hook. Yeah. Oh, you know. So, how can we picture such a structure? Well, you think about a model M of true arithmetic, and I will assume that it is in some sufficiently rich language, say language of piano arithmetic, where plus and times will be represented by relations. And then you take some element n and you consider a structure A whose universe is n, and I will identify n with numbers preceding it in the ordering, and then some relations on the structure which are definable in M. Okay. Now it is we will always consider the situation where we will have structures like this with some inbuilt structure of arbitrary, with no conditions on it. So without loss of generality, one can assume that there is one relation, k array for large enough k, which also encodes the, the graph of plus and times and successor. So in some sense, the language L contains the language of the big model M, of the ambient model M. Okay. Now, there is a little bit more to this picture, which will turn out to be useful. Because if you look at n, and then you take all numbers which are bounded by some exponential term of this form with k a standard natural number, so I will denote this initial segment somewhat loosely by this form, then this is a cut in the in the ambient model. It's a substructure, but it also serves the point here as a natural second order structure on the first order L structure which we have here. Okay, so this is the situation. So we have some A which has universe which is finite from the point of view of the model and can be and is typically non-standard number. There is some unknown relation which we simply do not specify in advance, but it's rich enough to contain information about the underlying arithmetic, and it will contain much more, perhaps. And then there are these points which are behind the universe, but every point which is bounded below a term like this is naturally identified with the L array relation on S. And so one may think that these points here in this cut are basically the second order objects on this initial pseudo-finite structure, second order objects from the point of view of the ambient model M. Okay, so this will be useful. So, and this is in one-to-one correspondence. Now let me discuss few examples of structures which will be of the interest. So we will want to eventually prove some things about lengths of proofs or sizes of circuits, and some discuss how you can define or prove some NP or co-NP properties of objects. So examples of structures of interest. So the first example will be, we always have this, there is this cloud of inbuilt relations which I won't specify, and then there will be some unary predicate U, and you can we will consider property where the ambient model M thinks that U has even cardinality. Now surely you can define this in Peano arithmetic, and you can define it even in a much weaker theory, or and the natural way how to define it is to say that on U there is a total pairing of its elements unless it's empty. Okay? And so what we will want to achieve is a situation where we take this structure, technology, we take this structure and start identically with this fixed pseudo-finite structure at the beginning. Now if you are identical up to n, you have to be identical up to 2n, up to n square, and so on. So we are identical a little bit longer, and then the model can divert to something else which will satisfy a theory which will differ from place to place. And what we will want to arrange is that in this model the cardinality of U is odd. So this will be a type of example and situation which we want to discuss, and it makes perfect sense. But the key property in this construction is that the structure itself will not change. What changes is after that, and therefore if you have here elements of this gigantic exponential size, then also you change the second order structure over the fixed pseudo-finite structure, but you do not change the structure itself. That's the key in all these examples. Now let me do another example. So we can certainly encode by some relations. We'll also encode a circuit in n atoms p0 up to pn minus 1, and you can then talk about having U a unary predicate on n, and having W a computation of U by circuit C on U by C, and this will be first order definable. So what I mean is that the relation between these three second order objects is first order definable, not W from C and U. Now in fact, as you all know, if C has extra property, namely that it has depth below some fixed constant, then in fact this W is first order definable from U and C. Okay? And so we might be thinking of situation where we have some circuit, and for example the circuit always produces value 1, and we want to add an input and a computation where suddenly it produces value 0 while preserving the initial structure as in that picture. Okay? Now the third type of thing which which is similar, is when we talk about propositional formulas and proofs. So we have this initial structure in the ambient model, and there will be a formula, a propositional proof. Now, a propositional proof is fairly generic concept, namely in the Kuhn-Krekov definition is basically a witness to some polynomial time property, but we can always reduce to the fact that the property is first order definable, and in fact in this talk I will think about propositional proof being simply the Hilbert style textbook calculus, modus ponens, some axioms, and the ordinary formulas. So you encode formulas and proofs, you write down the conditions, and then you might ask a question whether, for example, you can have a formula which does have a proof in this structure, but in the extension you will find a falsifying assignment. So want a falsifying assignment to a proved formula. Now, note in this case that if we can define that the size of U is even in some very fancy and complicated way, but if we define it in the simple way that there is a pairing on U, then the property that you change it going to the extension means that you do not preserve certain pi11 statement. And so let me write that what we get if we arrange such a thing. Sorry. And so this is a rather loose notation, but let me explain it. So this means that I have a model M where there are elements N, R, and U, and we think about this structure in the sense of M, and we also think of the second order structure over it as those which is definable in M. And then the same thing is here. So in particular, this structure is an element of M star, but you have a new second order structure over it. So it makes a good sense to speak whether or not you preserve second order formulas, and this will and this notation in this kind of informal formulation will mean that some statement which has a universal quantification over relations and then something first order becomes false when passing to this new ambient model M star. So what is the statement here? The statement is that there is no pairing on set U which leaves one point out. This is something which will certify that its cardinality is odd. Now because it's even here and we are in a model of true arithmetic, you cannot have two things at the same time, but you have it in M star. Okay? Yes?
So you're expecting being even in this pi one way, not a sigma one way.
No, I'm now talking about being odd. I'm expressing odd in the sigma 1 way, and therefore it's false in the starting model M.
Can you clarify, is U one-dimensional or is it K area?
Oh, U is a just subset of M. It's a unary predicate.
And what is the theory of M star?
Well, so that will depend on what we will want to get from it. So I'll get to a statement in a second. But think about it, as being, say, model of Peano arithmetic. Yes. Okay.
So what is confusing is that you write less than or equal to. I would expect that you just write is not elementary equivalent, but.
Well. Yeah, so that is confusing. Yeah. So that's good. At least it seems to follow what confused people pay attention. Okay, so let me get to the first example with some statement, and I will actually give its proof in order to show what might play a role later on. So this is example going back to ITI. Actually, I think that ITI probably could, maybe gave a similar talk 20 years ago. So I'm just reconstructing what he might have said.
Usually takes 20 years.
Okay. So here is the situation. So we have this model, and it's a model of true arithmetic. We have n, and we have arbitrarily built it in relation R on top of n. Okay. And so what we want to say is that for all such m, n, and R, there exists U, which is in M, and it is a unary predicate on n, such that first M thinks that the cardinality of U is even. Second, there exists M prime such that n, R, and U is in M prime. The structure n, R, and U in M is the same or isomorphic to n, R, and U as in M star. And third, M star is a model of sufficiently large theory, say Peano arithmetic. Now we will in fact see what we need, and we need much less for that to be true. So this is some situation. Now I will add here a condition that this model is countable to make later proof of it possible, or rather the type of proof I want to give. And now comes a theorem which is due to ITI, that the situation, well, let me write it like this, is true. Now, I'm not sure if this makes actually English language sense. So what I mean is that in every situation like this, this is valid. Okay? If and only if parity function is not in AC0. Like, yes. And for M star thinks that U is odd. Okay, yeah. Now, so ITI actually mentions in his, so parity is not in AC0, and this was proved by ITI in 83, and by First, Sachs, and Sipser. I think that the journal paper is 84. And ITI actually mentions in the introduction of his 83 paper that this formulation, that proving this situation is valid, was his original formulation for this result, and then only later on people sort of he doesn't say that, but people probably refuse to listen to that type of situation, and so this was the final result. But he somehow expresses the opinion that only those situations in complexity theory which can be treated in models of Peano arithmetic are those which can be solved at all. Now this might be a bit pessimistic at 83, but it's probably realistic in 2012, or maybe optimistic in 2012. Now, so let me now prove this theorem in order to show that one can approach this through some concept of saturation, and I think that this is something which has a bearing on a problem which we study now. So let me prove from left to right. So if you have a situation like this, and you in fact do have a polynomial size constant depth circuits, so there exists D such that for all say K or M large enough, there exists circuit Cm of depth d, size m to d, computing parity on m inputs, well, then you will have such a circuit in the model of true arithmetic as well for this parameter n, and the circuit will be simply part of the inbuilt structure. We can choose it arbitrarily, so we take it to contain this circuit. And then if you find a situation as in this picture, then if your theory M star is able to prove that whenever you have a circuit computing parity and it says that the set is even, then it cannot be odd. So how do you say that a circuit is computing parity? In the usual way, you know, on empty set it gives 0 and adding 1 point changes the value. Then how do you say that the value on U is 0? Well, you can say that because that is first order definable in the structure. And then if you know that you cannot have a parity circuit computing 0 on an odd element set, which you prove, which is true in the model of, say, true arithmetic, then this would be a contradictory situation. Okay. Now, so is this clear or semi-clear or non-clear?
I was just not sure where you're using assumption 3. In particular, if you
So what I'm
replace piano arithmetic by a weaker theory, what would happen?
okay, so I'm just going to comment on it. So what I only need is that in this model you have some basic theory like induction for first order formulas on this finite structure, plus a statement that what I just said is true, that if you have a circuit computing parity and it gives value 0 on some set U, then you cannot have a witness that it is odd. And this is a pi-1,1 statement about this finite structure. So it is in fact a bounded statement from the point of view of the Holt model if you have a large enough elements. But think about this as simply it's some basic induction plus 1 pi-1,1 statement. Okay, and this will be always the case. Okay. Now, so how does one go about showing the opposite? And so I want to show it just to describe the role of saturation which can play here. So this is not an argument which Aitai has in his paper. He has sort of bare hands type of construction there, but I think that it can be done in this way. So observation, which is fairly clear, is that these pseudo-finite structures, at least those sitting in the ambient model of true arithmetic, are recursively saturated. Okay. So now, let me just briefly define this in case people haven't heard this concept. So this means that if you have some recursive set of formulas, say phi1 x y1 up to yk, phi I x y1 up to yk, then it is true that if you, for any substitution of parameters from the set for these k variables, if the set is finitely satisfiable in the structure, then it is satisfiable altogether. So the recursive set here is important. This set is recursive. You can recover the ith formula by a recursive definition from I. Okay. Now, why is this true in these structures? Well, this comes down to two things, and they seem trivial in this context, but in a more general situation to which we aspire to use this is they are actually the heart of the matter. So the first thing is that one has a truth definition for the structure satisfying some first order sentence with parameters from n. Now, a truth definition in M. Why is that? Of course, the sentence psi can have unbounded quantifier complexity, but you are evaluating over a structure whose universe is n, and therefore, from the point of view of M, this becomes the quantifiers of psi become bounded by n. Now, there are also these relations which the sentence can use, and they have some definitions. We haven't specified that, but in fact, because it's over a finite structure, they are coded by some elements. So from the point of view of M, there is a bounded truth definition for formulas of certain fixed complexity, and if you remove the bound on complexity, there is a sigma 1 definition. So as long as you have induction, say for sigma 1 formulas, and in fact less is sufficient, then you have induction also for statements involving Tarski's satisfiability relation on this pseudo-finite structure. And now consider a statement for parameter, say t, for all I less than t, there exists x less than n, such that the structure n, oh, sorry, no, it's okay, except it should be the other way around. There exists x, such that for all I less than t, the structure n are u thinks that phi I xy is true, and so these y's are fixed in advance parameters. Okay. Now this statement is now a statement written in the language of M, and it's a property of T, and moreover it's satisfied for all standard T, because that's just finite satisfiability of the type we are starting with. And therefore by overspill or by induction it has to be true up to some non-standard T, and X witnessing the statement for some non-standard T will automatically witness it for the type, and therefore it will be element realizing the type. Okay. So this argument rests on two things. The first thing is that in this ambient model it's a simply huge structure, and you can define the truth definition, and you can formulate this as a property inside the model. So we need that this is definable, and then what is phi I is definable from I for this to make sense. And secondly, that you have enough induction there. Okay. So recursive saturation, it's kind of, I guess, classical or standard to talk about recursive types, but you won't change anything if you talk about, say, RE types, or on the other hand, you know, primitive recursive type, actually even polynomial time types. Okay. So in this respect, so these structures are very nicely behaved. Now, with recursively saturated structures, maybe I should have named from that this was invented by Barweis and Schlipp and by Risser in early 70s. So the nice property of these structures, if they are countable, is that they are what is called resplendent. And that means that if you have a sigma 1 statement now, which is consistent with the structure, with the theory of the structure, then you can actually realize the second order variable on the structure without adding new points. Okay. So classical definition first. So A is resplendent if and only if whenever phi R is an L together with R, well, not maybe R, say V or S sentence and it is consistent with the theory of A, then there actually exists its realization on A such that the expanded structure satisfies it. Okay. So what we look at the task to construct this set U and the example in Untitled theorem from these lenses. So remember that we have some n, we have some r here, and what we want is u also in M, which has the property in the parity example. Therefore, M will think u is even, and you have this extension where the parity changes. So think about this structure. You know, assume somebody gave you a u, and you look at this structure, and you look at its theory in its language, in the language L. And then we think of this statement as, this relation as being a statement that it is a witness that the cardinality of u is in fact odd. And then we have some fixed recursive theory, say Peano arithmetic plus soundness of some, simply whatever we'll need, we would put there. Okay. Now, so of course this looks like in a roundabout way, because we are supposed to get u, but before we get it by hoping by this construction, we actually should have it in order to to expand it. But what you look at it is differently. You will try to look at all consequences of this basic theory to gather the assumption that it is u, all consequences in the language of this structure. So there is a recursive set of formulas, and let me write it down so that it's clear what's going on. So let psi 1, psi 2, and psi k and so on. So let this be, say, the kth consequence, which is an L sentence. So let me write specifically that it has u and r in it. That follows from t plus u is odd. Okay. So this is a sentence in this language, first order sentence. And we think about it as being evaluated over the structure NRU. Okay. Now the point is that if you take these sequence of formulas, well, it's recursively enumerable, and by some standard tricks, by, for example, repeating a formula so many times that the number of the repeats encodes a proof or something like that, we can assume that it is in fact recursive, and then changing, then evaluating the formula, the sentence, over the finite, over the pseudo-finite structure. This simply translates into a constant depth circuit whose depth and size is essentially bounded by n to the power, to some power where the exponent is the quantifier complexity of the formula. So in other words, from such a sequence, you get a sequence of circuits whose sizes are, say, without loss of generality, the depth of circuit is at most k and size is at most n to the k. And these circuits have the property that they will be satisfied by all subsets of the structure which have odd cardinality. Okay? So now you look at the whole sequence together, perhaps taking the conjunction of first k formulas here, and then you extend it up to some non-standard number small enough with respect to n. Okay? And so what you had is a not quite AC0 circuit. You have a circuit whose depth is some d prime little non-standard number and size is n to d prime, again the little non-standard d prime, which has the property that it is valid on all sets of input of odd cardinality. Okay? And so now you have to use something, some combinatorial fact, and that's the assumption which the theorem gives us, namely that parity is actually not in AC0. So I'll use it in the following sense. So for every watt, say d, there exists nd such that for all, say md, for all m greater than md, for all circuit C, depth of C is less than d, size of C is less than m to d, inputs are x0 up to xm minus 1, and C is valid, gives value 1 on odd size inputs, then there exists an even size input which will also give value 1. Okay. So this is the parity for this is interpretation of the AC0 lower bound. Now this is a true statement. So we look at it in the ambient model M, it's true there as well. And so we apply it to this non-standard small d such that the md is smaller than equal to n. This can be done because going from here to here is a definable recursive function. And therefore we will know that there is in fact in model M, where is it? There is in model M some u whose cardinality is even, which however satisfies all the consequences over some fixed theory of the assumption that it is odd. Okay? And so this is what we take for the u. And now here comes the use of the resplendency, and one has to still do some work here, but which I will leave out, but let me remind you of the picture. So we have n, r, and here is this u, the nice u, and what we want is the structure extending this. And so we look at it as the problem in the resplendency. Namely, you think of simply this theory, say this phi s as a theory in some bigger language than the language of this finite structure, in particular in the language of this m star, and you simply take z as instead of phi of s, and what you will get is not the resplendency in the sense that you can expand the structure in order to interpret the new symbol such that this is satisfied, but that you can extend and expand the structure in a way that you do not add new elements in the initial segment. And for that is important that the structure is recursively saturated, namely every type which contains the statement that x is in the less than n, meaning in the pseudo-finite structure, is satisfied already in M. So in this construction, in the construction underlying this resplendency argument, the reason why you do not add new elements is that the structure is recursively saturated. What your kind of Henkin type construction forces you to add an element, it is already there. Now here it is already there if it forces you to add an element which is less than n. But if you do not, if that is not forced, then you might actually have to bring a new element to realize the Henkin construction. So this, in this sense, it changes a little bit, and there are other variants of it, and I want to mention that my student Michal Garlik is working out all these variants and applications of these things. Okay, so the summary of it, before I'll start the proper talk, is that it is interesting to construct an extensions of these pseudo-finite structures which do not preserve some pi1 statement about them, and that one might think that the saturation properties of this might be useful or helpful. Now there are two, at least there is an interesting example also due to ITI about the pigeonhole principle, and I will skip that, but I'll point out one other situation where the corollary is not that AC0 is not in, that parity is not in AC0, but that NP is different from co-NP. So let me explain this new type of situation, which if you arrange, you prove this type of statement. So here the situation is the following, an example. So again, I have some kind of inbuilt structure, and here I have a H relation, and model M thinks that the graph with this H relation is not 3-colorable. Okay. Now what I want to now arrange is a little bit more than that. What I want to arrange is a structure which will look identical here, and then it will be kind of maybe fatter than this, and only then it diverges possibly. Okay. So let me write it what I mean by this line. So again, the NE of M is the same as of M star. The initial segment from 0 to 2 to n, this initial cut in sense of M is a part of the same initial cut, the cut defined in the same way in M star. And again, M star satisfies some basic theory plus some, or maybe all, pi1 true statements about the first order structure. So let's say any true statement, and we do it for one by one. The first condition is that the initial segment doesn't change, that from the point of view of n and M star is the same. So okay, that all elements in the M, the wide ones, which are bounded by some 2 to the n to k for k standard, are also in M star. But there might be more, excuse me?
Structure?
Well,
need to preserve structure?
yeah, so we have to, we assume that our language L contains these basic relations in you know, arithmetic, some arithmetic language, plus and times relation, and so that has to be preserved. So as a substructure, but not elementary or not the first order theory. Okay. And so the statement is now that if you can actually arrange a situation like this, then this is equivalent that NP is different from co-NP. So what?
I said, and M star thinks that graph is three colorable.
It is not three colorable.
But M star thinks it is.
Oh yes, of course, I'm reading out these. No. But I'm happy that actually there are people paying attention. And, so that was a test. Okay. So observation. This situation is possible if and only if NP is different from co-NP. Now, so why is that? Well, so if NP would be equal to co-NP, then you have some NP definition of non-three colorability which is valid in true arithmetic, therefore also in M. And so for the specific graph E, which is not three colorable, there would be some witness, well, some witness V here witnessing that it is not three colorable. And so as long as you have this witness relation, some first order binary relation definable between E and witnesses W, and as long as your model M star satisfies that this witnessing relation is sound, whatever it witnesses that it's not three colorable is actually not three colorable, then this leads to a contradiction. Okay. Now the opposite implication is proved by some kind of similar argument which I outline here, again based on recursive saturation, but now you think about deriving pi 1 consequences of being three colorable. Now this is fishy in context of resplendency, but in fact it is all right here because we are talking about sigma 1 and pi 1, but it is not a sigma 1 and pi 1 in the real world. It is in fact something first order definable in the ambient model. So one can make this precise and, and to use similar arguments. So what would be the situation here is that you would have a NP circuit which is supposed to accept all non-three colorable graphs, then it also accepts some three colorable graphs. Okay. Now the problem with this type of argument is that where do you get the suitable graph E, and then if somebody happens to give it to you, how are you going to go around to proving that such a situation exists without actually having the result that NP is different from co-NP? So I'll just in the remaining time just outline the situation to which one can reduce this question, and where sort of the hardness of this task in front of us is moved from complexity theory to some saturation properties in terms of model theory. So the general situation we will now have, again this is a model of true arithmetic, and there is some R, and there is also some F, a relation which codes say a 3CNF, such that in M it says that it thinks that it is not satisfiable. And so what we want to do is to extend this in a way that we add a satisfying assignment and we preserved enough some basic theory plus enough pi-1,1 statements. Okay. Now, so you know, when I said before that we don't know what type of graph take, so do we now know what type of formulas or tautologies or unsatisfiable formulas take? Now there is a certain theory in proof complexity of the so-called proof complexity generators, or one should perhaps say generators of proof complexity, which does give such an examples. And I will not talk about this theory at all, but I will right away give the type of example and the model you get from it. So what this gives you is the following situation. You will be given a formula which is not satisfiable, and it is of this form. Sorry, we want 3 CNFs. And so these are n bits. Just not that you become nervous, I'll just take 2 minutes, okay? You know, the director's 2 minutes. So these are n bits, these are polynomially many bits in n, and all the variables in different YRs are disjoint, so the only variables which appear in 2 or more formulas are the x's. And the situation will be that this is not satisfiable. And so what one can construct now is a model M where this formula becomes satisfiable in some sense. So this is this F, namely in the following sense, that there exists some u such that for all I less than n there exists vi such that phi I u vi is true. Okay. Now, to get this model, one needs to use some unproven assumption in complexity theory, namely that one-way permutation exists. And the drawback of this is that this model will unfortunately not be a model of true arithmetic, but only of fairly weak arithmetic. It will have induction, say, for all polynomial time predicates, and it will satisfy all true pi-1,1 statements about the finite structure, but it will not be a model of piano arithmetic. There won't be even the exponential function total and things like this. So what one needs from this situation is to mimic the constructions using the recursive saturations to get the model which would look as follows. So what we want is some n prime such that again it has the properties as before, so n are f So as before, we want to extend this structure together with its second order structure over it in a way that we add no new elements here, and we add possibly new sets and new relations, but we do not remove of any. And what we want here is that in M star there exists some W which collects all these witnesses Vi together. Okay. Now, of course, if n was finite and you have finite number of witnesses, you can define W. But if n is non-standard and you just have infinitely many of them, you do not have a, say, first order formula which would define the W. So you need some collection properties or replacement type property in the ambient model to get this. Now, we don't have such a properties in M, but there seem to be that there might be enough saturation properties. And so one would like to add this W by a resplendency type argument. And for this you need three things. First is some version of saturation. And well, maybe one needs more things, but let me know just about two. So you need some form of saturation in M. And then you need to know that the theory whose model you want to find is actually consistent. And in those earlier examples, the second part is the hard part. That's where you need to know that MP is different from co-NP or parity is not an AC0. But here it is actually easier using some propositional proof complexity if we use this assumption together with assumption that NP is different from that NP is equal to co-NP. Now this sounds fishy, but let me just finish the argument. So if we establish enough saturation properties of M, this would lead to this construction and it would be a contradiction. And so the complexity theoretic type result of that would be that the existence of one-way permutation together with MP equals co-MP is inconsistent. Namely that MP different co-MP follows from this cryptographic assumption. Now in a big picture this is not out of question because many other complexity theoretic assumptions like P equals BPP, P different from NP, cryptography possible and so on, they follow from assumptions of this type which says that all circuits doing certain specific tasks has to be large. And this is just one assumption of that form. So, and that's what I would be really interested in, some result like that. So let me summarize. So what the investigation or the problem I'm thinking about is now how much saturation in M1 can arrange. Now there are three constructions of this M, and two give saturation by some general model theoretic argument, and that I somehow feel is not enough. And then there is a third construction which actually gives a model which is Aleph1 saturated, but it's modulo some hardcore lemma which is conjectured but not proved. And so, these expansions of structures where the underlying second order object have some fixed complexity and adding a new object which does something, this goes under the name of dense model theorems, and these hard-coded lemma is very much connected. So I'm certainly not claiming any theorem as you have seen. I'm just saying that at this point, today I don't see where is the point why it doesn't work, but may change by tomorrow. It did change many times before this talk. So, okay, thanks very much.
Is there one quick question?
In your model where you make the even set become odd, how much agreement between M and M star into that cut do you get? So they agree up to n. And
they have to agree up to any power of n, but they will not agree up to 2 to the n because there will be this contradictory pairing already. So they won't agree much.
Yeah, I think looking at the time, we leave further questions for the break. And let's thank Jan again.